All right, let's get started. So this is our last lecture, as I said, and what I wanted to do today that I mentioned earlier is I'm just going to give a brief lecture, maybe 15 or 20 minutes, with some thoughts for you about all the topics that we talked about and how I hope they'll be useful to you in your future. And then I'm going to open it up and leave maybe 20 or 30 minutes for some open Q&A. I'm happy to take any questions about any topic that's on your mind and you're interested in, or you think your classmates might be interested in, on machine learning or probability or statistics or modeling, or on data science or careers or anything like that. So start thinking about any questions you might have, but I'll start with the lecture. So I just wanted to give a little bit of a, like I said, an overview of the course and how I think it will be helpful to you in your future. So this is a foundations course, meaning that I'm hoping this course gave you more than necessarily an understanding of how to use the exact methods we talked about, although I hope you got an understanding of that as well. I'm hoping this course gives you an understanding of the internals of all the methods we talked about and how to break them down and how you could potentially tweak all the different components of a given algorithm that you might see out there, such as logistic regression, to fit whatever problems you might be facing in the real world as you go on to your careers in research or maybe starting a company or working at a company or any of those things. So first, let's think about kind of the old way of doing some kind of machine learning or data analysis. And let's use this as a running example. Perhaps we're a doctor and we get information about a patient, maybe what symptoms they report, maybe some test results, cholesterol, blood pressure, genetic sequencing, any of those things. And we want to make medically relevant decisions, perhaps decide, do they have heart disease? How might they respond to various drug treatments and whatnot? But of course, this I think applies to all sorts of problems from medicine to finance, business, maybe what directions you want to take a company, what products you want to sell, advertising, logistics, how you want to ship things around, all those things. So so I think this is kind of the old way that I've written on this slide, which is you get your data and you have a library of algorithms that you can plug it into. One of them is logistic regression, another one is support vector machine, another one is a hidden Markov model, and then you plug it in to the algorithm and you get some results. And like I said, I think this is kind of an inflexible way of doing data analysis. In particular, sort of copying someone's work is you're saying, I hope one of these off-the-shelf algorithms exactly fits my need that I see in my application. And if it does, then I'm great. But if it doesn't exactly match, then I'm kind of stuck. It's kind of like the difference between knowing how to code versus being able to use Microsoft Word and Microsoft Excel and PowerPoint. If what you want to do is the thing that's implemented in one of those software programs, then you're great. But if you want to do something more complicated and you don't know how to do any coding, then you're kind of stuck. Okay, so here is maybe kind of the better way, and hopefully it's been clear to you guys that this is kind of the way I'd like you to think about doing data analysis and machine learning in the future. So there's a bunch of steps. So we're a doctor. We're trying to figure out what's the best way to go about diagnosing our patient. There's a bunch of steps we have to take. And I think we want to go through these steps for every type of data analysis we want to do. The first is to identify variables. That is, what are the properties of each patient? That could be, like I said, the symptoms. Do they report feeling tired? Do they report fainting or something? As well as what test results you got. Maybe you do blood pressure. And then also the things we'd like to do inference about, like, do they have heart disease? How will they respond to a given drug treatment? And I think you can divide variables into 3 types, which is always observed variables. These are things that we've observed for every patient. In machine learning, we usually call these features, the features of an example. The never observed variables, or sorry, the sometimes observed variables, which are things that we've observed for some patients, but not for others. So these are usually our labels we would think of in a classification context or a regression context. That is, for some patients, we've done the perhaps very invasive tests to determine, does this patient have heart disease? And perhaps we'd like to set up a classification problem that asks for the other patients, meaning for those patients that have had the invasive testing, that can be kind of our training set. Our other patients are our test set, where we want to infer from the less invasive tests, do they have heart disease or not? So again, those are often our variables. And then we have never observed variables. These are things we'd like to account for in our reasoning, but that we don't observe directly. So that could be, for example, one example of a never observed variable is if we're doing some kind of clustering. We think our patients are divided into some type of clusters based on all the information we see about them, but we never directly observe that cluster label. So that's something we want to do inference about without having ever observed it. Another example would be if we believe perhaps there's a batch effect in how we're getting the test results. Maybe we think that we're getting blood pressure, say, measurements from different labs, but we don't know what. But we've lost. You know, the hospital isn't reporting who the technician was, and we think who the technician was might be important. So we might want to estimate that internal bias in the blood pressure measurements. Or similarly, maybe we're getting blood pressure measurements from each patient over time, and we think there's some underlying healthy blood pressure for each patient. But of course, that's sort of a theoretical thing. We can never observe that directly. So we could observe that, for example, by seeing what their blood pressure is over a long period. And maybe what we want is to see if we can observe what the healthy value is over that long period. We can look for changes away from that healthy blood pressure. Some more examples would be any kind of like latent representation estimation that we see a lot, for example, in deep learning these days. That's in some sense a never observed variable. So we can never, it's something we'd like to do inference with. We think it's valuable for understanding what's happening with our patient, but we can't see it directly. And then perhaps another distinction would be care versus don't care. That is, there are some variables that we care about. That would be our whether or not they have heart disease or not, or perhaps the clusters. Maybe that's something we care about. We really want to maybe tell the patient if they're in the high risk cluster versus the low risk cluster, so that they can change their behavior accordingly, versus don't care. That those would be variables that we need to do inference about because we think they're important to the variables we care about, but that we don't care about directly. So for example, that bias estimate would be a good example. We don't care really directly about the bias in the measurement. We just have to account for that in our inference. And by the way, sometimes the variables that we care most about, we can never directly observe. One would be heart disease, right? Heart disease is kind of a concept that we made up. We can observe some fact about a patient's heart, if we do an autopsy or something, but those are just kind of consequences of the underlying fact of whether or not they have heart disease. So we might want to, it might be that the thing we care most about, we think has some dependence on the things we can observe, but we can't observe that directly. Another example, this is true of sort of all diseases, I would say. So, we can't necessarily directly observe if a patient has cancer. What we observe is whether or not a tumor grows or shrinks. And from that, we do some inference about whether or not it was cancerous. Say, or we look at it on a slide and under a microscope, I mean, and see, what shape do the cells have. Based on that, and what we know about biology, we could do some inference about whether or not they have cancer. Okay, by the way, please feel free to ask questions. Okay, step 2 is we've identified our variables. Now we need to formulate a model. That is, we need to decide which variables are dependent on which, what's the probability distribution that governs those dependencies. That is, if one variable is dependent on 3 others, what is the specific distribution that defines that variable as the function of the others? And then what are the parameters of that distribution? And then in all those cases, we have to decide, is that something we want to learn, or is that something we just want to define ahead of time? So usually it's the case that we'll define ahead of time our dependencies. That is, I say, okay, so I think blood pressure is a function of heart disease. I think there's some dependence on, if you have heart disease, that will influence your blood pressure somehow. I might further say that I think it's specifically that's governed by a Gaussian distribution. And then, depending on how much I believe the biology, how much I kind of want to depend on my pre-existing understanding, I could say that, okay, I think someone with heart disease will have a mean blood pressure of X, and other patients without heart disease will have a mean blood pressure of Y. Or I could say those are parameters that we want to learn from our data set. And then, of course, which we decide to learn versus infer is going to depend a lot on how much data we have. Because if I have almost no data, I can't afford to learn a lot of stuff just because there's not enough data to make that inference. So, if I'm a solo doctor and I have 10 patients, well, I probably have to just formulate this model ahead of time. I probably can't afford to learn any parameters and just plug the model into my probabilistic inference for each patient, not trying to do any inference. Versus if I have some giant database of patients, of patient data that I can work with, well, maybe I don't even have to decide what's dependent on what. Maybe I get to do network learning. That is, maybe I can learn the dependencies in my Bayesian network just straight from the data. That's a topic we didn't talk about a lot in this course. We didn't have time, but learning the structure of a Bayesian network, there are algorithms for that. Oops. There we go. Also, the model that we formulate often has to depend on what we can afford to do computation for. So we've seen a bunch of examples of that in this course. For example, when we did feature selection for, let's say, logistic regression, we said that we would love to use, for our regularization, we'd love to use the L0 loss. That is, just penalize ourselves for each feature that we include, because we're trying to encourage the model to pick fewer features. But we said that it's not convex and it's hard to optimize. Therefore, instead, we put on a L1 loss. And we made that choice not because we thought it was exactly the right choice in terms of exactly what we think is happening in the real world. It's that that's what we could afford to compute. Another example would be a hidden Markov model. Perhaps, let's say we get cholesterol measurements over time for each patient. Well, we might think that there's some complex dependence. Maybe we think that their cholesterol from today depends on their cholesterol from 1 year ago. Like maybe there's some patterns across years. But we probably couldn't afford to do inference over that, because as we said, that would give us a high tree width model, and that would be hard to do inference over. So maybe we just say, okay, today's cholesterol depends on yesterday's cholesterol, and that's all we can afford to do computation for. Okay, then as we've talked, we've gone through a bunch of different specific models in this course. We talked about linear models for classification and regression. We talked about how to regularize those with lasso and ridge regression, L1 and L2 regularization. We talked about naive Bayes and Gaussian discriminant methods, and then we looked at lots of different Bayesian networks, Markov random fields, and for example, a mixture model that you might use for clustering. Of course, this is just a small subset of kind of the example models that you'd see in the wild. But I think all of them you can put into the same framework. And in fact, I encourage you, when you see some, maybe you're reading a paper about some model, like how does this expressed as a Bayesian network? Maybe it's done explicitly in the paper, or maybe it's not. Just to give you a taste of this, the most common way is models might have a complex dependent structure among variables. So for example, what is a decision tree? How does that compare to the existing methods we have? Well, we can think about it. Well, it's kind of like it's a classification method. It definitely is. We're definitely imagining that our label y is a function of our variables x, but the specific dependence function is something more complicated. It's this tree structured function that first looks at one variable, then looks at another variable, and so on until it gets to a leaf. So this thing here, this dependence, is the kind of unique part about a decision tree. And then you can realize the same for lots of different methods. What are lots of clustering methods? Or let's take a latent representation clustering, for example. Well, that's usually imagining that we have some latent representation, and we're imagining, I'm not going to draw all these arrows. So this is our latent representation. Here's our observed features. And what that method is saying is that we're imagining that our latent representation is generating our features according to some complicated function that's defined by that method. So again, I think it's really valuable to figure out how each method fits into kind of this generative framework. How is the method imagining your data is generated. One way that's really valuable, I think, is that often once you realize what the assumption is of how data is generated, often you can see that it doesn't make any sense. For example, you'll see often that a machine learning algorithm will use a squared error loss. And they say, well, of course I'll use squared error. It's just simple, makes sense, why not? But you know that what is squared error loss? Well, it's really, we talked about this in the course, it's really the log likelihood of a Gaussian distribution. And maybe you look at the thing that they're applying that squared error loss to, and you say, wait a minute, that's not Gaussian distributed. It's not even close to being Gaussian distributed. Perhaps we should pick some other loss function to optimize rather than squared error. That's just one example of how I think it's useful to think about how the model is formulated according to a probability distribution or a Bayesian network. Okay, I talked about this. Here are just some examples of other methods you might see in the wild. Okay, step 3, we've figured out what our variables are. We've formulated how we think they're dependent on one another. Our next step is we have to do optimization or inference over those variables. Our first choice is, are we going to determine a point estimate or a posterior distribution for each variable? So we've said that we usually have a case like this, where we have some number of variables per example, and then we have some parameters that are shared across all examples. And we said it's most common that we want to do, oops. There we go. It's most common that we want to do inference over the per example variables. That is, we want a posterior distribution for those versus we want a point estimate for our variables or for our parameters. And there are a couple of reasons for that we talked about. The first is that there's much more uncertainty in per example variables than there is for shared parameters, because we have so much less data to learn the values of those per example variables. Also, recall that in general, it's much more expensive computationally to learn our parameters because they, in some sense, tie together all of our variables. So whatever tree width that we're looking at, if we're including parameters that are unknown, that's going to vastly expand the tree width of our model, and therefore increase the cost of our inference. Okay, and so right, so first thing is we have to figure out a point estimate or distribution. Second thing is we have to figure out what type of inference we want to do. And I've sort of ordered these from most effort from our end at the beginning to sort of set up the algorithm versus the least effort at the beginning, but the most effort for the computer when you're doing the inference itself. So the most effort for us as the person setting up the algorithm is to get a exact inference solution or do an analytical solution for optimization. So if we can take the derivative, if we can figure out how to find its optimum, then that's awesome. Then usually inference is really easy per patient or per example, because again, we just plug it into this exact solution that we found. Versus the hardest thing for the computer to do is to do a 0th order optimization. So again, an example that would be a grid search, where we just, for all the things we want to do inference over, we just consider a bunch of possible values, plug them in to our objective function or our probability distribution, and then look at how that how the distribution changes as a function of a variable. We didn't say this explicitly, but MCMC is, you can think of a 0th order optimization algorithm, because again, it's just plugging in values for different for our different variables, and then trying a different value and seeing does the probability increase or decrease. And then in between those, we had for example, first or second order optimization algorithms, for example, gradient descent. That's iterative, so it's still a lot of work for the computer, but if we do the work of calculating the derivative, that's much more efficient than doing grid search. Likewise, if we do EM, we had to do our exact inference for our 2 steps, our E step and our M step, so we had to work that out mathematically. But once we do, we said that EM is usually extremely efficient and gets us very close to the global optimum, although it doesn't get us exactly the global optimum because we need to get an analytical solution to do that. And we didn't say this explicitly, or we didn't talk about this topic too much, but EM, I would say, is a category of algorithms that you would call coordinate optimization that alternate optimization steps along various coordinates. In the case of EM, that would be over our auxiliary variables and over our parameters. Okay, and our last step is to apply the method and evaluate its performance. I think this is often the most important step, but often the most neglected step in practice. So let's take classification as an example. So the simplest thing to do is I've made my classification algorithm. I want to ask, how good do I think it's going to be when I apply it in the real world? Well, so first thing I need to do that everyone knows, hopefully it's very familiar to everyone in this course, is you need some independent test set that you haven't looked at when you're doing all your inference, both in the inference that's in the method and also any kind of parameter or hyperparameter selection that you might be doing. You have to have that test set separate, because of course that's going to be your estimate of how it's going to do in the real world. So I'll apply it there and I'll get my accuracy. And something that I think people who do classification are pretty familiar with at this point is that accuracy tends not to be a very good measurement, because false positives and false negatives often are not, they don't have the same importance. So how do we think about importance? Well, we talked about this when we talked about decision theory. That is, I'm going to make some choice in the real world, for example, what drug to give my patient. And I have to think about what is the utility, like the goodness, how much better or worse is the world after I make this choice, as a function of what choice I made, and as a function of, for example, whether or not the patient actually had heart disease. And of course, giving a patient a drug that they don't need if they don't actually have heart disease, versus not giving them a drug that they need when they do have heart disease, those two things are very different in their utility, meaning how good or bad they are. So if you're doing classification, people have come up with all these ways, which actually, in my opinion, aren't the right way to do it, but they've become kind of field standard, which is, okay, let's do an ROC curve, and maybe we'll calculate the area under the ROC curve. What we're really saying there is, well, we don't know what the best threshold is to choose our cutoff of how confident the model has to be before we say that, yes, the patient does have heart disease. So we're just going to average over all the possible thresholds we could make. And that's good, at least. It's a little bit better than accuracy in the sense that it's not giving us a single, it's not giving us a single threshold, but you're kind of punting on the question of how what's the relative utility of false positives versus false negatives. So I think the right thing to do in the classification context is to decide that up front. What's the cost of a false positive? What's the cost of a false negative? And then I will choose the threshold that optimizes my utility. And so that's what we talked about when we talked about decision theory, or more generally, if this is some more complicated thing, like for example, what dose of a drug to use, well, that's going to depend both on what's the correct dose and how bad is it to be a little ways off. Like maybe it's okay to give a higher dose, but really bad to give slightly too little dose. So that would make you want to slightly overestimate the dose. And we can incorporate that into our decision making, and we talked about how to do that. Okay, so those are our steps. Like I said, I hope you've been realizing that this is something that I'm trying to instill in you throughout the course, which is I hope that having a deeper understanding of kind of the probabilistic and mathematical basis of all of these machine learning algorithms that we talked about in this course and that you see elsewhere in the wild. I hope that you having a deeper understanding will let you break down these steps and tweak the method or come up with new methods for the problems that you see in your career going forward. Okay, so that's all I wanted to say for that. We have around 20 more minutes. Please feel free to ask any questions you have. Any questions, like I said, about the topics of this course, maybe anything you're still confused about, anything you'd like to know a little bit more about that we can talk about in the next 20 minutes, or any questions you have about maybe how these topics relate to something else you've seen, or questions you have about the career or anything like that. This is sort of our chance to have fun at the end of this course. So please do type your questions or feel free to unmute and ask them. I got one question. What topics will be covered in CMPT 983 this fall taught by you? Will it be remote or the in-person format? Could you please introduce the course a bit more? Yeah, okay, so this is a course, I'm not sure the number is right, but Martin, Esther, and I will be teaching a course in the fall called Applications of Deep Neural Networks. This is a seminar-based course, so it's really intended for grad students who are interested in doing research. So, it's designed to help you get up to speed with the current research in this topic, so that you can go out and do your own research. So the format of the course is, thanks for asking this, because I hope lots of people in this course will be interested in that course, is we're going to give a couple of lectures, not very much, of a bit of a background on neural networks and what's going on in the field right now. And like I said, this is focused on applications. So this is not so much, this of course is not so much focused on how to perhaps do optimization in neural networks in some really efficient way that you would be interested in if you wanted to do research on how to do neural networks in general. This is a topic on how you can use neural networks to advance research in whatever your specific field of application is, whether that's biology, medicine, vision, natural language processing, any of those things. So like I said, we're going to give a couple lectures, just a bit of background. Specifically, we're going to be giving background on a couple of topics that we're going to be focusing on, sort of subfields. And we haven't finalized these, but we're going to have a couple of subfields that we're going to focus on. One of them will be representation learning. Another will be interpretation, that is that is explaining neural network choices and what that tells you about perhaps the importance of each feature. Those are two. There'll probably be one or two more that we haven't picked yet. So again, in those first few lectures, probably 2 weeks, we'll give some background on that. Then we'll have a couple more weeks, probably one more week, where we talk about communication. So this is a skill that's really important for grad students, I think, which is that your research is only ever as impactful as your ability to communicate it to others. And I think a skill that is easy to miss as a grad student is being able to communicate well. That is both verbally and written. So we're going to talk about both how to give a good presentation and how to write well in science. And those skills are going to be useful to you because next thing I was going to say is you're going to be doing a presentation and a report for the course. So so the next part of the course is going to be you're going to pick a paper on some topic that you're interested in and present it to the course. So that should be a new paper, just in the last 5 years, and you'll present it to the course and try to give it in a good communication form. So that's again one of the targets of this course, is to help you learn to give good presentations. So that'll be the middle few weeks of the course, and then for the last few weeks and leading up to this, you're going to do a project. So that is, you're going to aim to advance the state of the art in this field. Usually what students do is they make some modification to the paper that they presented in the first part of the course. Now, of course, now we hope that these papers or these projects can turn into papers that are ready to submit to say a conference and be published in a machine learning venue. That's that's a bit ambitious to do in one semester, but we'd like you to target that, to have the first steps towards a paper. And in our past years, we've done that, and there have been a couple of papers that have come out of projects started in the course. Okay, I hope that tells you about that course. Yeah, please do come. I think it'll be of great interest to folks in this course, and it should be a good time. Another question. A question is regarding 983, the course we were just talking about. Can you enroll as an undergrad? We are open to it. Please send us an email and ask. It'll be harder to do as an undergrad, certainly, than, for example, this course is to do as an undergrad. A question about rejection sampling. I've been wondering about rejection sample. We would do the steps to gain a sample and compare U times C QX less than P of X, and we do this to estimate P of X, but how do we compare without first knowing P of X? Could you provide some examples for using rejection sampling in the real world? Right. So this is something perhaps we glossed over quickly, which is, remember that when we're doing inference, the thing that we don't know is the normalization constant. So we know what we called in the course, I can write this down here. We know P approximate X, where this equals 1 over Z, or sorry, I'll do this the other way around. P of X equals 1 over Z times P tilde X, where we don't know what the 1 over Z is. So again, this comes up most often when we have evidence. So for example, if we have some probabilistic model where what we want is, we want to know P of X given Y, where Y is a whole bunch of evidence. As we know, this equals probability of X comma Y over probability of Y. This thing is usually given to us. That's our Bayesian network. So if what we wanted was probability of X comma Y, well, it'd be easy. We just plug it straight into our Bayesian network and get our answer. The hard part is this, right? Because to get P of Y, we said we have to sum over all the possible values of X, probability of X comma Y. And especially if like this is a large number of variables, or again, as we said when we were doing inference, if there are lots of variables that we have in our network that we don't care about, that would make us have to do a sum both on the top and the bottom. In those cases, that's going to give us this unknown constant factor at the bottom, and so we don't know what that is, and it would be very expensive to find out what it is. So recall that when we did our rejection sampling, we did it based on this thing. So we were only using the unnormalized probability, not the normalized probability. So that's what we're using to define our rejection for our rejection sampling. Let me know if that answered your question. Any other questions? Anything you're curious about that you think your classmates might be interested in?
I have a quick question. I thought it'd just be easier to use a mic.
Go for it.
So I guess for someone who's going to the workforce, we've learned all these techniques and we can apply them. But I was wondering if in your experience, you have trouble maybe translating this into more layman terms for maybe clients or stakeholders, and how have you gone about tackling that?
How do you translate all this material into layman's terms? This is a fantastic question. And this is something that I see a lot, or that I deal with a lot, because as I didn't talk about this a lot, but my field is computational biology. So I work a lot with biologists who maybe don't have a really deep understanding of machine learning or statistics or probability or any of those things. And this is, I think, a topic that is worth spending a whole course on. So as grad students, there's the writing course. We talk about writing in our seminar course that I was just talking about. So, and really, this is a skill that I think I'm still building in my career that you want to build across your entire career. A couple of just general thoughts about this. So one is to really focus on the inputs and the outputs. So often it's the case that, let's say I can't come up with some great machine learning method. And I could, if I'm trying to communicate what I've built to someone, I could take them through all the alternative, all the internals of, okay, here's what happens when it gets a patient data example. Well, first it puts it through a Bayesian network, and here's what I'm doing with EM learning and all this stuff. But of course, that's going to be very hard. You know, you almost have to give them this whole course to communicate that to them, which in some cases is what you want to do. But in more cases, they're interested in the inputs and the outputs, meaning what information is it taking as input, and then how is it framing the output? And in addition, they'll want to see how you've evaluated it. For example, what's its accuracy, and this goes this is very closely related to this question of evaluation and decision theory, which is they want to see, for example, how many false positives versus false negatives, and you want to make an argument of, here's what I think the trade-off between, for example, false positives, false negatives is, and here's how it did on my test set, and therefore here's how I think it's going to perform in the real world. And then, of course, again, this is simple when it's a simple classification problem of, let's say, disease or not disease, but it's much more complicated when it comes to, let's say, coming up with a recommended dose for a patient. Oh, by the way, another I think angle that's often useful is you say, what assumptions have been baked into this model? For example, I'm assuming that blood pressure depends just on heart disease and nothing else. And if I've made that assumption, then all the rest of the details of the method follow. And that can be a good place to talk about with someone, because they can go back and forth with you about what the assumptions are, even if they can't necessarily on the model internals. But again, like I said, this is a big field. Hopefully that helps.
Yeah, thank you.
Just a few minutes left. Any last question? Okay, let's stop it there. This is our last lecture. The only last thing for the course is the final project. By the way, I'll be releasing all the grades so far, including the participation on courses, just so you have a couple of weeks to check it and make sure it all looks good. But otherwise, good luck on your final projects. And I just wanted to say thanks to everyone. This has been a great semester. I really appreciate all the attention and engagement you put into this course. Everyone's done a really great job. I really appreciate how everyone has worked with their group mates, and you guys have supported each other and asked for help from me and from Hung, and I think that we've had a ton of great communication, and it's been really great to be able to watch everyone to grow and learn. So that's been great for me. And so again, thanks to everyone, and good luck with all your future endeavors.